So, okay. So, hello everyone, and welcome to the week 9 of the problem solving session for the discrete mathematics course. And this week, what we'll do is we'll look into generating functions. Okay. So, right. So, for example, let's look at this. Let's look at this series 1 plus x squared plus x cube and so on. And this is a geometric progression, and we know that this is an infinite sum, and we know that this is given by 1 over 1 minus x. And yeah, and if you look at the coefficients of this polynomials of this polynomial, I mean, this is not really a polynomial, but yeah, if you look at the coefficient of the terms here, then what you have is you have a 1 here, you have a 1 here, and so on. So the coefficient of every um, um, yeah, um, every term is 1 here. So in this case, you say that 1 over 1 minus x is a generating function for the sequence 1 1 1 and so on. Okay, so there are different kinds of generating functions that we looked at in the course, and we also saw in the lectures, and we also saw why it is important. So what we'll do today is we'll try to do some illustrative examples for the same. So yeah, okay, so let's start with the first question, which is quite simple. So yeah, so you have this series 42 42 42 and so on. So earlier you saw that this sorry this 1 1 1 1 and so on can be generated using this function. So similarly, can you find a generating function for this series? Right. So good. So the answer is 42 over 1 minus x, and that is simply because you know that 1 minus 1 1 over 1 minus x is 1 plus x cube, x squared plus x cube and so on. So if you multiply this thing by 42, then 42 over 1 minus x is same as 42 plus 42x plus 42x square and so on, and that basically gives you the sequence 42 42 42 and so on. Good. So in general, you can replace 42 with any number a, and you'll get the sequence corresponding to a and so on. So right, good. So right, so you're given this generating function, and this is an infinite function. So what you want to tell is you want to tell the sequence that is generated by this. Right. So yeah, you are right. So the answer is C, because you have 2x cubed plus 3x to the 5 plus 4x to the 6 and so on. So the coefficients of the terms before this would be simply 0. So therefore, if you collect the coefficients, you get 0 0 0, 2 3 4 5 and so on, um, which is this option C. Good. So right, so you can try this one. So you want to find the generating function for this series 1 1 3 3 square 3 cube and so on. So okay, so let's try to solve this. So you have 1 over 1 minus okay, let's say you have 1 over 1 minus um, x, and this is equal to 1 plus x square plus x cube and so on. And now let's say you replace x with ax, then what you get is 1 replacing x with by ax, then what you get is 1 minus ax is 1 plus ax whole square plus ax whole cube and so on, and that is 1 plus ax plus a square x squared plus a cube x cube and so on. So essentially you're generating the sequence a to the 0, a to the 1, a to the 2, a to the 3 and so on. And in this case the a that we're looking for is 3. So therefore 1 over 1 minus 3x would be the generating sequence for this, which I think does not match with any of the options. Yeah, sorry about that. Sorry, so this maybe I'll change one of them. Sorry. So I think you might have also gotten the same thing. I don't think it is equal to any of the other expressions there, right? Yeah, but okay, maybe if I just change the question slightly and yeah, if I don't want this sequence, but let's say I want it 9, 27, 81 and so on. Then what would how would you change this this generating sequence to get that? This part was clear, right? This part was clear, right? Okay. Then how would you modify this to get a generating sequence for this? Okay, so let's try this. Um, 9 over 1 minus 3x. So that would be 9 times 1 plus 3x plus 3 square x square plus sorry 3 cube x cube and so on, and that would be 9 plus 27x plus 81x square plus 729 x cube and so on. So essentially you're getting this sequence, right? 9, 27, 81, 729 and so on. So this would be a generating function for the sequence given by this. Is this okay? So we are just using the part 1 which you already answered, the first question here which was pre-multiplying with an a, and we are just using it and combining with the 2. Is this fine? Okay, good. So yeah, so next is maybe I'll just write down the formula that we saw in the lectures. So sorry, yeah, so in the lectures we saw that if you look at 1 minus x to the minus n, where n is a positive integer, then if you expand this thing, then the coefficient of x to the r in the expansion of 1 minus x to the minus n is given by n plus r minus 1, choose r. So this is the formula that we saw in class. So using that, can you try to solve this one? Okay, good. So let's identify the value of n and r for us. So n is 10 here, and r is 5 because you want to find the coefficient of x to the 5. So r is 5 for us. And now we can just use this formula. So for this n and r, what you get is 10 plus 5 minus 1, choose 5, which is 14, choose 5. And if you expand this, you get 14 into 13 into 12 into 11 into 10 by 5, 4, 3, 2, 1, and this cancels out, and this term cancels out. So what you have is 14 into 13 into 11, and this turns out to be 2002, like you said. So A is the correct answer. And just to recall how we got here, so I mean, there are other ways of deriving this, which are maybe more mathematically precise, but what we did in the lectures is, you looked at this binomial expansion. Okay, I'll take a new page. So just a quick recall, what we did is we looked at this binomial expansion, and we know that we've seen this earlier in the first lecture, that this is same as n choose 0 plus n choose 1x plus n choose 2x square, and so on, n choose n x to the n. And now what you do is you replace x with a minus x. So what happens is you alternatively get minus terms, because the even ones would cancel off the negatives, and the odd powers of x will retain the negative sign. So 1 minus x whole to the n is same as n choose 0 minus n choose 1 times x plus n choose 2 times x square, and so on, right? And this will be n choose r minus 1 to the r x to the r, where r is from 0 to n. And now what you do is you try to replace this n with a minus n, and then these terms will act differently, and you can just find a general you can find a general formula from there for the r term, and that will turn out to be n plus r minus 1 over r. So right, so so that's as we discussed in the class. And so let's look at the next question. So you are given this polynomial, and you want to find the coefficient of x to the 14 in this. So maybe try this out once. Okay. Okay. So let's try to solve this. So what you can do is, as a first step, you can see that x to the 4 is common to all the terms. So you can pull this out. So this is same as x to the 4 times 1 plus x square plus x cube whole cube, and this is same as x to the 12 times 1 plus x square plus x cube. And what you want to find out is, you actually want to find out the coefficient of x to the 14. And notice that you already have a multiple of x to the 12 here. So whatever term you get here is always going to be multiplied with x to the 12. So essentially you are looking for coefficient of x square in the expansion here, because if you have the coefficient of x square, say ax square, then you're going to multiply it with x to the 12, and that will give you the coefficient of x to the 14, which is what you want. So essentially the question is, what is the coefficient of x square here? So one thing that you could do is, you could write them side by side and try to um, yeah, I mean, one way to do that would be one sorry, yeah. And now what you could do is, you can look at all possible ways in which you can get x square. So x square you can get if you take x square from here and 1 from here, 1 from here, um, right, and okay, right, and or you can get it if you take an x from here, an x from here, and a 1 from here, and so on. So um, right, so essentially you're looking for the all such possible combinations that will give you um, um, yeah, that will give you x square. So um, right, so okay, maybe we'll note this down explicitly also, but let's try to use the formula that we did in class. So I'll come back to this, and we will do this manually also, but the formula that we did in class is, so you have 1 plus x square plus x cube, and you're looking for coefficient of x square in this. And um, yeah, so what you can do is, um, you know that 1 plus sorry, you know that the series 1 minus 1 over 1 minus x is same as 1 plus x square plus x cube, and then there are infinitely many terms here. Okay, so what we're doing for the moment is, instead of looking at 1 plus x square plus x cube as a polynomial, we're going to replace it with additional terms here. So what this will look like is, this will be 1 plus x square plus x cube and so on. So for each of them we do this. Okay, so then essentially what you're doing is, we're doing 1 plus x square plus x cube and so on to the 3, and we know that this is equal to 1 over 1 minus x. So this will be given by 1 over 1 minus x cube, which is same as 1 minus x to the minus 3. And now we will use the, so I have not justified right now why this is not affecting. We will see this, but let's first calculate and see what the answer is. So now you know this from the formula that we just wrote. We know that the coefficient of x to the r in the expansion of 1 minus x to the minus n is given by this. So now we will apply this formula. So now what is the value of n? N is 3. And what is r? R is 2, right? Because you're looking for the coefficient of 2. So this is given by n plus r minus 1. Choose r, which is 3 plus 2 minus 1. Choose 2. And this is nothing but 4, choose 2, which is 4 into 3 by 2, which is 6. So right, so if you follow these steps, then you'll get the answer of 6. And the only thing that I've not justified right now is, why is it enough to why is it that we're not doing anything wrong by adding these terms, is that you're only adding these higher order terms. So you are only going to add x to the 4, x to the 5 and so on. And when you multiply this guy, say x to the 4, with even the smallest term in the next there are 3 copies of this, right? If you multiply it even with the smallest term in the next copy and the smallest term in the next copy, you're only going to get a coefficient of x to the 4, which is anyway larger than what you wanted. So it's not even, so there will be some additional terms here, but you're not interested in that, because you're only looking at the coefficient of x square. So is this okay? Okay, good. And if you try to do it this way also, you'll get the same answer, because you can choose x square from here and 1 1 from here, or you can choose x square from here, 1 1 from here, and x square from here and 1 1 from here. Similarly, you can choose 2 x's. So you could choose 2 x's from here, the first bracket, the second bracket and third bracket. You could choose it from here, or you could choose it from here. So these are the only 6 possibilities that will give you a coefficient of x square, and that also justifies the answer of 6. But yeah, the reason we did not do this explicit thing is because in this case it was easy, because you only were looking for the coefficient of x square, and this was also relatively small. But if this were like something like 3003 and I was looking for coefficient of 1507, then looking at all these possibilities will be very difficult and time taking. So therefore it's this trick is very useful in that sense, because then you are just doing one step of calculation and you are getting the answer. So this is a nice trick that can be handy at various places. So the answer for this is 6. Okay, good. So right, then we'll move on to the next question. So the question is that you're given sorry you're given 3 lines here. This is the first line, this is the second line, and this is the third line. And in the first line there are 3 blocks of word, RA, PA and A. And then you have 3 blocks of words in the second line and 2 blocks of words in the third line. And what you're going to do is, you're going to construct words from this in such a way that you will take one block from the first line, one block from the second line, and one block from the third line. So you will do, say for example, I can take RA from the first line, I can take C from the second line, I can take E from the third line. So that will be one word. I can also take PA from the first line, I can take C from the second and E from the third. So this is also a word and this is also a word that you can construct. Also you can take A from here, N from here, E from here. But this is not the kind of word that I'm interested in, because I'm only interested in in the number of four-lettered words such as this and this. So the question is, how many such words can you make where you have two constraints? One is you can only pick one word from each line. Second is it has to be a four-lettered word. Okay, so maybe just try this out for some time. Okay, so what is your idea? Maybe would you like to share?
Ma'am, from the first line, there are two ways in which we can pick two letter words. Uh, Plus, there is one way we can pick a one letter word, and multiplied by, from the second line, we can pick one letter word in two ways and a two letter word in one way. And from the third line, we can pick a one lettered way in two ways. So 2 into x power 1. So we have to find now the coefficient of x power 4 in 2x square plus x power 1 whole multiplied by 2x power 1 plus x square whole multiplied by 2x power 1.
Right, right, good. So, okay, so what you're saying is you will formulate this whole problem in terms of polynomials. So, the idea is that um, what you do is for the first line, you come up with a polynomial which looks like this: x square plus x square plus x. And what this means is there is a two letter word here, which is what the power here denotes. There is another two letter word here, which is what the power here denotes, and there is a one letter word, which is what the power of x here denotes. Similarly, you do this for the second line. So second one would be x plus x square, because you have two letters, two blocks of one letter and one block of size 2. And then you have in the third line you just have two blocks of length 1 each. Now what happens if you multiply the polynomials is that when you look at this x square and maybe this x and this x, if you multiply them, you will get a four letter word, which is because the coefficient this corresponds to the letter PA, and this corresponds to C, and this corresponds to E. So and the term for this is exactly x square into x, which is x to the 4. So each um, each way of getting x to the 4 gives you a distinct letter of size 4, and therefore it's sufficient to find the coefficient of x to the 4 in this given polynomial. So therefore it's sufficient to find the coefficient of x to the 4 in x square plus, okay, I'll just rewrite this. So x square plus x square is 2x square plus x, and this is 2x plus x square, and this is 2x. And maybe I'll take out some terms outside. So you get x cube times 1 plus 2x times x plus 2, right? And it's same as finding a coefficient of 1 in this, and which is finding coefficient of x in this block, because x cube is already outside. So that you can get either by multiplying x with 1 or by multiplying 2x with 2. So this whole thing you'll multiply with 2 because of this term that you pulled out outside, and that will give you 1 plus 4 into 2, which is 10. And yeah, that is exactly what Akansha also solved, right? So the nice thing about this approach is that it generalizes very nicely. So if I give you any number of lines and any sized blocks here, maybe 3 lettered blocks or 10 lettered blocks, and I want to find some uh, 42 letter word, I can just do it simply. It generalizes, it does not depend on how large n is, it just simply gives you the answer in a very nice way. So yeah, so this is a nice example of why polynomials are useful in counting. Good. So yeah, using the similar idea, can you try this out? So this is something that we did in the first lecture also, which is that stars and bars counting sort of thing. But this time maybe try to solve it using polynomial method. So there are 4 candidates and you want to distribute 10 votes to them. So basically what we mean is you have C1, C2, C3, C4. It's possible that the first guy gets all the votes, other gets 0, or first guy gets 1, the other guy gets 1, this gets 3, and this guy gets 5, and so on. So you just want to find the total number of ways in which these votes can be distributed. Okay, good. So sorry. um yeah, so can you spell out the polynomials that you got?
Ma'am, 1 plus x square plus x cube plus so on plus x power 10 whole power 4. The coefficient of x power 10 in that.
Right, good. So you have 1 plus x square. So the number of ways the candidate 1 can get votes is either he can get he or she can get a vote of 0, which is what x to the 0 would mean here, or he can get a vote of 1, which is what the power here denotes, and or they can get a vote of 2 and so on, but up to 10. they can't be they can't get 10 11 votes because you only have 10. Similarly, for the candidate 2, candidate 3, and candidate 4, you get the same um, yeah, you get the same polynomial. And like we did earlier, what we'll do is we will multiply all of them so that you get all possible ways in which the votes can be distributed. So here you have 4 candidates, therefore you raise this to a power of 4, and what we're interested in is the coefficient of x to the 10 in this equation, because yeah, x to the 10 essentially tells you that the 10 votes have been distributed. It could be that 7 votes are distributed to the first one, 2 to the second, and 1 to the third, and 0 to the last one, and so on. So we just want to find the coefficient of this, which would tell us all possible ways in which the votes can be distributed. So this is same as what we did earlier. It's the same logic, and now we will just use our formula. So which is that this is same as 1 minus x um, to the minus 4, and yeah, so n is 4 for s and r is 10, so you have n plus r minus 1, choose r, which is 13, choose 4, and sorry, this is 13, choose 10, sorry. Yeah, r is 10 for us, so this is 13, choose 10, this is 13, choose 3, and that is same as 13 into 12 into 11 divided by 3 into 2, which is same as 286. So yeah, so you're right. So the answer is B, 2 and 6. Okay, so now let's tweak the question slightly. So um, instead of distributing the votes um, howsoever I want, now additionally I'm adding a constraint that um, each of the candidate must get at least 2 votes. So it's so something like this would be discarded. So something like this, which worked earlier, is not valid now because there are candidates that don't get at least 2 votes. So so definitely the number that you're looking for will be much smaller than what you got earlier because you're only reducing the number of ways. So just try this out. So just take care of the additional constraint that each of them must get at least 2. Okay, so let's yeah, okay, good. I think yeah, the answer is right. So let's solve this using the same idea of polynomials. So let's first write how many ways can you give votes to the candidate. So the candidate can get 2 votes or 3 votes or 4 and so on all the way up to 10. So note that we have deleted the terms corresponding to x and 1 because now you have this additional constraint. So you can either get 2 or more votes. Similarly, same thing happens for C2, C3 and C4. And now we are going to multiply this like we did earlier. So you get x square plus x cube plus and so on up to x to the 10 whole to the 4, and now you're looking for coefficient of x to the 10 in this. And now what you do is you take out this x square in common, so x to the 8 comes out and you have 1 plus x square and so on up to x to the 8 whole to the 4, and you're looking for coefficient of x to the 10 here, and 8 is already outside, so essentially you're looking for coefficient of x square in this bracket term. Whole to the 4, and now you know that this is same as 1 minus x whole to the minus 4, so n is 4, r is 2, and again you get n, the coefficient as n plus r minus 1, choose r, which is same as 5 choose 5 choose 2, which is same as 10. So yeah, so your answer is right, which is 10. Okay, good. So now what we did is we just added one constraint on the towards the left side, so we deleted some terms from the left. Now let's add and impose a additional constraint that there is an at most condition also. So okay, maybe just one condition for now, so let's impose the condition on the other side, which is at most. So now say you have there are 5 children, c1, c2 and so on, c3, c4, c5, and you have 12 action figures. You want to distribute among them so that no child gets more than 3 action figures. So something like first child gets 4 and then 4 4 4 0 0. This is not valid because I can't give 4 action figures to any child. So yeah, so the question is again, in how many ways can you do this by respecting this constraint? So yeah, any ideas how do we proceed with it? Maybe how do we write the polynomial corresponding to C, the first child?
1 plus x square plus x cube.
Right. And then you have the same thing for the 5 children. So you will raise this to the power of 5. And you have 12 action figures. So you are interested in the coefficient of x to the 12 in this. So, right. So, yeah, you do the same thing again. You know that this is same as 1 minus x to the minus 5. Sorry. So, n is 5, r is 12. So, what you get is n plus r minus 1, which is 16. Choose 12, which is same as 16. Choose 4. And this is same as 16 into 15 into 14 into 13 by 4 into 3 into 2 into 1. So this is 2, 5. So this is 14 into 13 into 10. Right, so you also got the same thing, is it? Yeah, is this fine? Okay, I don't mean this is equal, but yeah, I mean it's sufficient to find coefficient.
Ma'am, but plus x power 4 will also contribute if we take it infinite series. It will also be counted where one child gets 4 action figure or 5 action figure.
Mm.
So that violates the constraint of at most 3.
Hmm.
So can we write it as 1
Heterogeneous.
by
Sorry, can we write this as?
we like 1 by 1 minus x we can write if we assume the whole series to be
Yeah, yeah,
infinite,
yeah.
but if we write plus x power 4 x power 5, so
Hmm,
one
hmm.
child getting 4 action figures will also be counted.
Right, right. I agree. Yeah.
So
So,
how do we write it like 1 by 1 minus 6? Can we do that? I don't think so.
yeah, yeah, I think, yeah, you're over counting this way because you're also calculating the terms like x to the 4 that you mentioned. So, so how do we get around that? Okay. Mm, okay. So, hmm. Okay, so one thing that you could do is very naive, which is like a lot of counting, but one thing that you could do is you can subtract from here the so you have 1 plus x square plus x cube. This is there 5 times, right? And you're saying that it could happen that there is x to the 4 here, and that is getting multiplied with, say, x cube here and other terms like that, which I don't want to count because um yeah, because yeah, I mean, we have this constraint that, sorry, we have this constraint that no child gets more than 3 action figures. So my proposal is, okay, one thing that you've done is you have counted total ways in which um, total ways in which you can distribute 12 action figures. And now the problem with that is you are doing overcounting because you're counting things like this. So right, so one thing, um okay, maybe like one simpler thing would be, rather than overcounting like that, you just multiply all of them and look at the coefficient. So maybe that would be easier than counting the whole thing and then subtracting. The subtracting way is that, um, assume you're taking x to the 4 from here. So there are a lot of things that you're going to have to subtract. Assume you're taking x to the 4 from here, and then look at the coefficient of x to the uh, 12 minus 4, which is x to the 8, in the remaining expression. So you have 4 terms here, which is 1 plus x square plus x cube whole to the 4, and you're looking for coefficient of x to the 8 in this. So uh, right, so this way what you're doing is you are only subtracting the ones that were bad because of this. And yeah, that is not enough. Then you'll also have to subtract the ones that are bad due to x to the 5, but there is some overcounting that is happening in between. So this is somewhat like pi, that um, the principle of inclusion exclusion that you saw. So you can think of this as different sets that are bad due to 4 x to the 4, that are bad due to x to the 5, um, that are bad due to 6, and so on up to x to the 12. And what you want to find is you want to find the union of them. So you want to find the total number of bad elements that are there because of either of them or any combination of them. So essentially you're looking at a union of them. So you could do something like a pi here, but yeah, I mean, you don't need to get there because it looks a bit complicated. I don't know if there's a simpler expression that you can come up with, but yeah, for this example it's sufficient to just like you said, you can just expand this out and then look at the coefficient of x to the 12. So that would be simpler than doing this overcounting business. But yeah, good for pointing this out. So yeah, so maybe I'll say this is not correct because there is some overcounting that happens. So okay, so that is one way. But okay, do you also have any other way of doing it in a simpler way? Okay, then maybe I'll also think about it. But yeah, good for pointing it out. So okay, so I'll move on to the next question. So you have um, 4 police officers here, and you have 25 donuts that you want to distribute to them. And the condition is that each of them gets at least 3 donuts, but but none of them can get more than 7 donuts. So what would be the, let's write down what would be the polynomial for the first policeman.
X power 3 plus x power 4 plus x power 5 plus x power 6 plus x power 7.
Right, and this will happen for all the 4 of them. So this is what you have, and you are interested in the coefficient of x to the 25 in this. So we will do the usual trick. We will this x cube is common amongst all of them, so you take that out. So you have x to the 12 times 1 plus x squared plus x cube plus x to the 4 whole to the 4, and we are looking for x to the 13 in this expression. And I think, like you said earlier, I think we can't approximate this because yeah, because again there could be terms that you end up that end up giving you this power of 13, but you have yeah, I mean, you might have taken a 5 or 6 from somewhere. So right, so yeah, so then probably like one way would be that you just expand it out. At the moment, yeah, I don't have any third method that may be better than this. mm. Okay, okay, so I'll think about this. So, but yeah, the polynomial that you need is just this, and you are interested in the coefficient of this. So, one way would be expand, but I'll think about it if there is any better method for finding the coefficient for this. Okay, so we'll move on to the final question. So, you have 3 varieties of dosa. You have plain dosa, you have masala dosa, and you have onion dosa. And you want to choose 12 of them. You want to choose 12 of them, but in a combination. But additionally, you are making sure that you're taking at least 2 of each kind. But for the onion dosa, you're not taking more than 3. So, what would be the polynomial corresponding to that?
Ma'am, x square plus x cube plus x4 plus so on plus x to power 12 uh,
Hmm.
whole square into x square plus x cube for the onion dosa. Whole square
Mm.
and
Okay.
coefficient of x to power 12 in this.
Hmm. Okay, good. So you're saying we are looking for coefficient of x to the 12 in this, but now the thing is, can it not be that you're getting x to the 12 as follows? So you are getting x to the 12 because um, because let's say you chose uh, 8 from here. So this is, maybe I'll color this is correspond, okay, sorry, I'll write it again. Then the other one is again x square plus x cube, and the third one is x square plus x cube. So this is for your plain dosa, this is for masala dosa, this is for the onion dosa. Yeah, and that is so the individual polynomials are right, but my question is, you can get x to the 12 in the following way. You could take, oops, okay, you could, okay, okay, so yeah, so you could maybe take x to the 8 from here, and you could take x to the 4 from here, and okay, okay, that, okay, fine, you don't need, right, that is fine, okay. So you don't need to worry about this x's being heterogeneous, because you are always going to make sure, anyway you're going to multiply them, so you're forced to either pick 2 onion dosas or 3 onion dosas. Similarly, you are forced to pick a masala dosa from this range and a plain dosa from this range. So yeah, I think you don't need heterogeneous variables here. And yeah, then you're right. So this expression can be written as x square times 1 plus x times x to the 4 times 1 plus x plus x to the 10 whole square. And yeah, um okay, so okay, mm, okay, so again like you said, if you um yeah, if you again try to approximate this, then you will end up hmm, then you will end up um no, sorry, I think this is fine, right? Because the at most condition here that you have is for the onion dosa, and that term is anyway here, so I can still approximate this, because here you only have at least two wala condition. So okay, so I'll maybe write what I'm trying to say, then let's figure out. So this factor comes from the onion dosas, right? So that means you're taking um, yeah, if you choose one here, then you are looking for, if you choose one, then you are looking for coefficient of um, x to the, so originally you wanted 12, 6 is already here, then you're looking for coefficient of x to the 6 in the expression here. And if you choose x, then you are looking for coefficient of x to the 5 in this box. And I'll just sum up whatever is the answer for this and whatever is the answer for this. I'll just sum up the coefficients. So my claim is that you can do your approximation business on this, because you don't have this utmost condition that was stopping you from approximating in this. So my claim is you can do it this way. So you can do 1 minus x to the minus 2, and coefficient of x to the 6 would be n is 2, r is 6. So this is 7, choose 6, which is 7. And if you're looking for coefficient of x to the 5, then n is 2, r is 5. So you are 6, choose 5, which is 6. So my claim is that you can do this in 6 plus 5, 6 plus 7, which is 13 ways. So do you agree with this, or is there a problem? Okay, good. Okay. Okay, so that's all that we had for today. Um, but yeah, if you have any questions related to the assignments that you want to discuss, then yeah, you can either write it into the portal that we have on the Swayam, or you could directly write to me on this. So next time I'll discuss all the questions that you have mentioned. So I'll just post the email ID. You can either write it here or you can use the chat. Okay. Okay, then next we will meet on 27th, same time, 6 to 8 p.m. Okay, thank you, Akansha.